Hi, I'm Chris Kanish, and this is CS361, Systems Programming. Today, we're going to be talking about the most popular application protocol of them all, the Hypertext Transfer Protocol. This is the protocol that underlies the web, but a whole lot of other things as well, and we're going to see what makes it special and the basics of how it works. So first and foremost, HTTP is an application layer protocol, right? So on top of our link layer, on top of our network layer, on top of our transport layer, we have our application layer protocol. So it uses the socket API to send and receive messages of variable lengths and specifically relies on TCP to make sure that those messages are reliably sent and received in the correct order. Within the application layer protocol of HTTP, there is still, as one would expect, a set of rules for how messages are created. Within HTTP, there are also requests and responses, just like you would see in something like, say, TCP. And what's special about these requests is that every single request that you create, it might be split among multiple packets, but it's still one request, is going to have all of the information needed to craft the response and send it back to the client. This becomes very, very important when it comes to the scalability of HTTP. Another thing is that when you create an application layer HTTP connection to an HTTP server, you can make one request and you'll receive the response back within that same TCP session, but you can also make another request within that same section, or maybe even several requests all at once. And the HTTP protocol is such that the server will send back in the same order the responses to the request that you made in that order. There's some message framing issues there, where we need to know where one response ends and the next response begins, where one request ends and the next request begins, but there are ways to do that in the HTTP protocol. And finally, just to get through the other important fundamental aspects here, clients initiate the connection, so they make the connection to the server, as you kind of have to as a client. Then the client speaks first and sends its request data that actually goes through at the application layer. So as soon as I connect, I don't wait for the server to tell me something like, hello. I immediately send my request with all the information needed to service it. And that request consists of a verb indicating what action I want to perform and a resource path that I'm going to use to signal what resource I want to access. And then additional metadata like what protocol version we're using in HTTP, and metadata like what types of files we can accept, what cookies we have for that server, things along those lines. So just as one slightly minor but still important point, there's a lot of what the web is not, what HTTP is not. This is another one of those vocab word sections where we go into how these different ideas relate and what their definitions are. So HTTP is the application layer protocol that browsers use to make requests. Browsers, more technically termed user agents, aren't always the graphical things that we see like Chrome or Brave or Safari. Sometimes they are command line programs like curl or wget. And sometimes you can even create your own HTTP request yourself simply by being able to run the protocol and type the individual bytes into your terminal. HTTP is the protocol you're going to use to make those requests. Browsers contain logic to make HTTP requests, as well as parse the responses. Some of them are hypertext documents. They can request new files based on what was in that hypertext document. They can run JavaScript. They can use CSS to change how things are styled. They can download images or videos and show those to the user. All of that is done by the browser, or as I probably should have put on this slide, the user agent. That's the proper name for it within the protocol. The web is kind of putting all of this stuff together, where we have the HTTP protocol, we have web browsers, we have web servers, and we have the other things that are needed to make that work, right? We've got the IP network, we've got TCP, we've got DNS. You put all of those things together and you can do the web. So the web is all of these things put together. And one of the most fascinating aspects of HTTP is that it is a pretty robust, useful protocol. So much so that many, many mobile applications, probably a vast majority, do all of their communication using the HTTP protocol. They aren't going to be a browser, but they are going to connect to a web server that gets connected to a database that runs some business logic, whatever have you. Web servers are kind of the are kind of the main way to provide a service on the internet in the modern age. This is one of the big topics that I cover in my course CS484, which unfortunately won't be offered next semester. But if you do get a chance to take it, I highly recommend you do if you find any of this stuff interesting. So the best part here is that HTTP is pretty general purpose, and the scalability that it gets out of having every request encapsulate everything that is needed to respond to it is probably why it has been used so widely in so many different situations. So there's not a huge amount that I want to add on top of what is covered in the book in terms of just like basic facts about how HTTP works. I've got a screenshot of Wireshark pulled up here, this amazing tool that you can use to record and interpret all of the messages that your machine is sending or receiving through the network. And right here, I've got highlighted one individual message that is an HTTP message encapsulated inside TCP, encapsulated inside IP, encapsulated inside of Ethernet. And this one message is going to have the application layer information for it. And that one message corresponds to this piece of information here. One other thing that Wireshark allows you to do is to follow a conversation. So here, I've got red as the things that the client says, and then blue as the things that the server says. So what you can easily see is the verb that we talked about here, where in a request, you've got verb, resource, version, headers, blank line. Those are the things that define an HTTP request. What defines an HTTP response is going to be version, response code, and response code meaning that those bytes usually just get thrown away. And then a collection of headers, a blank line, and the body of the response. In the most basic version of HTTP, as soon as the server has finished sending its response, it will close the connection. So in a normal, standard, basic server, you send that response. As soon as you have successfully called send on the last byte of the file or whatever it is you're sending, you then call close, and you wait for the next connection to show up or whatever it is your server wants to do. This allows the client to know how many bytes there are in a given response because they're going to read, they're going to read, they're going to read, they're going to read, and eventually they're going to try to receive, and they're going to receive a 0. They're going to say, aha, that must be the end of the file. I've received the whole thing. I'm happy. I got it. Let's go. That's not always going to be the case. One thing that HTTP allows you to do, as you see here, is pipeline requests. And so we end up with a framing issue where we say, okay, well, we used to rely on the fact that we were at the end of the response to know when the response was done, but we can't do that here. You just have to wait for the next response to start coming in. And I don't know where this response ends and this response begins. Like, yeah, in this case, technically, the server stopped sending messages, but one really important part of networking is that we can't know whether somebody doesn't have anything else to say to us or whether somebody does something to say to us, but the network has died and isn't sending packets. This is one of those fundamental problems with networking where you don't have some other way to ask, hey, are you okay? Because you're using that same medium to talk to the other side. So you very fundamentally have to have a distributed protocol that helps you keep track of what's going on. So in this particular case, and in every other case where you're allowed to reuse the same connection with HTTP, there will absolutely be a content length field, like we see here. So this content length header tells the client, hey, the next 648 bytes that you receive from me are the response. Once you have gotten to the end of those 648 bytes, you know that my response is finished. If you were doing a basic HTTP 1.0 server that closed the connection at the end of the conversation, you wouldn't need that content length. It'd be nice to put it there, just in case you wanted to, but you don't need to put that there. And you simply need to close that connection. For the purposes of homework 5, the other important headers that we have here are the host header. This is necessary for HTTP 1.1, and every client that is connecting to you is going to send that host header. On the server side, for our purposes, there's only one header that's really important, and that one is content type. Every single file that you're sending over, yes, it might have a name. Like this one doesn't have a name. This one is just the resource that's stored at the root of this server. But some things like favicon.ico are files that have a file name. One important thing about web servers is that they're not necessarily going to rely on the client to figure out what to do with a file based on its extension. That can actually be kind of dangerous to your computer if you think it's going to be this file type, but it ends up being that file type. What happens instead is that the server will tell the client explicitly, hey, the thing I am sending you is HTML text. It is encoded using UTF-8. This allows the client to know what type of file to expect and how to interpret it. In addition to the content type, there's also a content encoding. By default, a very basic web server isn't going to compress that response, but you are allowed to compress the response by passing it through gzip. That's not required for the assignment, but this is a very common important component to the modern web. We have our content type that tells us once we have decoded whatever has been sent to us, whether we're decompressing it or unchunking it, whatever have you, this is what type of file it is. Content encoding tells us how it has been transformed to be transmitted over the network. We also have important information for HTTP purposes, but not Homework 5 purposes, like the last modified header, which allows us to keep track of how recently something has changed. So if we want to ask for it again, we could send a message with the if modified since. So if we as the client have kept a copy of that file because we looked at it recently, we can tell the server, hey, only send it to me if it's been modified since October 17th, 2019. And the server might say, oh, hey, this hasn't been modified since then, so you can keep using that same version. And the server will respond back with an HTTP/1.1304 not modified. And that's much cheaper than sending the entire file or reading it off the disk, whatever have you. And that allows your web browser to render the file just that much faster, as well as preserve your network bandwidth. So you can imagine that this example is serving static files out of a directory, and that is at a basic level one of the first things that anybody's web server actually does. Usually the most basic version of an HTTP server is just going to say, point me at a directory and serve all of the files out of that directory. But the HTTP protocol itself doesn't say that's what you have to do. It's very generic. It says, given a request for a resource, give back a response. It doesn't say anything about how those should happen. The most common default things are to serve files out of a file system hierarchy. But a slightly more advanced version that you're going to be doing in Homework 5 is running a child process when a specifically formed type of request comes in. So just like you could decide to pull in the bytes from a file and send them out to the client, you could also take whatever that input was, which could be the requested resource as well as the headers, and then fork a new process and send those requests as input, whether through an environment variable or through standard in, and then connect standard out of that child process to the socket you've created that's connected to the client, and just let that child process send the bytes back where it thinks it's sending them to standard out, but it's actually sending them through the network because you use dupe2 to copy those file descriptors through. This is one of the coolest things that you can do with file descriptors in Linux, and that's going to be one of the big things that you're going to do in Homework 5. We've got a good amount of skeleton code around it, so it shouldn't be the nastiest thing in the world, but it is still pretty cool to see your web server kind of orchestrate all of these child processes and let them do your bidding to serve whatever your application is supposed to serve. And a system like this kind of allows you to write some code on your machine, then let anybody in the entire world take a look at it, use that code. That's one of the awesome things about the web, right? And it's awesome, but then it's also terrifying because yes, you can let your friend or that friend or that friend or that friend take a look at this cool code you wrote, and all they have to do is go to your website. But any attacker can also go to your website, and if they are able to do things that you don't expect, maybe they can take over your entire web server. So this is all to say that typically you don't just fork a child process and then connect these two and let them do whatever you want. That's a little bit inefficient, and it is actually kind of gonna be easy to shoot yourself in the foot and allow others to run arbitrary code. A more advanced and much more common use is to use a thing called a web framework, which is a library in a programming language, and basically every programming language has a web framework or several web frameworks that allows you to write code that determines what to do based on the request. And it'll also have a huge amount of helper functionality to kind of keep track of users, form your responses properly, deal with caching, deal with cookies, things along those lines. So we had these four definitions at the very beginning. And one other thing that I want to kind of expand on from the book is that the first three of these are no longer true about modern HTTP. The HTTP that we have in the book, I think, is version 1.1, which has been around since the 90s until it was the main version until probably the early 2010s. But nowadays, HTTP 2.0 is very, very common. I wouldn't say that it's more common than 1.1 on a per server basis, but on a per packet flowing through the network basis, HTTP 2.0 is probably more popular because it's used by big things like Netflix and YouTube. And honestly, after you've got those two, you probably have a majority of all the packets in the United States internet at least. This is all to say that 1.1 and 1.0 are these very basic text-based protocols where everything gets sent as part of every single request and everything comes back all in this nice ASCII text that's easy to debug and easy to look at. But there's a lot of inefficiencies in the way that that works. And so a lot of these things have changed going from HTTP 1.1 to 2.0, and now we even have HTTP 3.0. So in 1.1, we have a plain text protocol built on top of a reliable byte stream protocol like TCP. In 2.0, we get rid of this plain text protocol part. Instead of being a plain text protocol, we pack everything in a way that makes it very easy to compress. So if we go back over here to this is an HTTP 1.1 conversation, and this hasn't really been decoded in any way. All that these bytes are on the screen right here is the visual representation of those ASCII bytes. This HTTP 1.1 space 200 space OK carriage return new line is exactly what is showing up in the actual raw bytes of the connection. There is no extra decoding happening here. This is just stripping off the transport and IP and link layer headers and just shoving the rest of those bytes into a plain text visualization of the bits that are flowing through. So HTTP 2.0 removes that plain text protocol component and packs everything in a way that makes it much more efficient. And HTTP 3.0 actually builds it on top of a protocol called QUIC, which is a advance on top of TCP that still does reliable transport, but does it in a both more secure and more efficient way. So traditionally, every single one of these requests is going to include all the information needed to serve it. So if we come back over here to our example again, this is all in one individual TCP connection. And so there's completely redundant information here. So this time I asked for hostexample.com. This time I asked for hostexample.com. This time I accept gzip and deflate. This time I accept gzip and deflate. This time I'm using English. This time I'm using US English. I'm super, super redundant here, which is really, really good because it allows for scalability. If I had some server on the back end that, example industries, I could say, oh, I have so many requests coming in. I'm going to send some of these requests here. I'm going to send some of these requests here. And so then you have this front end server that multiplexes the requests among different servers. If everything needed to service an entire request is encapsulated within that request, I can just start sending them to whatever server I want. And as long as those servers are set up to handle those requests, they will handle them, send the bytes back, and I can send them to whatever ultimate destination they're supposed to go to. This is good for scalability, but again, really, really bad for efficiency. So in HTTP 2.0 and 3.0, the requests are going to include this information, but a lot of the times they're going to include pointers to the information rather than the information itself. So there's a thing called header compression that is happening there. We're going to say, not only are we going to make the headers tinier by just compressing the bytes and representing them with fewer bits, we're also going to take the same repeated header over and over and over again and say, hey, just refer back to those bytes that were earlier in this connection. We don't want to send the same exact bytes over and over and over again. We want to be more efficient and more fast. Finally, the other thing that has changed between 1.1 and 2.0, in 1.1, we have this first in, first out. 1.1 is first in, first out buffering. One request comes in, one request goes out. This is really, really inefficient because we might have a really, really slow request that takes a lot of CPU time and then a bunch of really, really fast requests that came after it. And those might not need any CPU time at all. I might be able to send them right away. But because I have to respond in order, the request that takes a lot of CPU time has to finish before I send the rest of them. In 2.0, we can multiplex requests and send them simultaneously so that any request that the client wants to make can all be initiated at the same time. And the server can say, hey, I'm going to respond to request number 1 right now. I'm going to respond to request number 4 right now. I'm going to provide you a few bytes from request number 2 right now. This is probably one of the biggest advantages that we get out of HTTP 2.0. And finally, the fact that we're using a verb and a resource and additional metadata is effectively the same. HTTP 2 and 3 are built in such a way that your web server that serves the requests that it receives can easily interpret HTTP 2.0 just by translating it back to 1.1 and then responding to it the way that it normally would have responded to it. That's how these things are typically implemented, so that this minimizes the additional complexity. You don't want to start over again because you're effectively doing the same thing based on the same rules in your application based on the fact that you got a bunch of headers and a resource and a verb. But in 2.0 and 3.0, the way that they get sent to you is going to look a lot different. So that's all I have for you today. This is everything for the networking unit. I know this is a huge amount of vocab and there's a lot going on here and there's a lot of moving pieces that kind of fit together. The most important part that I want you to take away is kind of what's cool and what's interesting about these things. And if you found any of this stuff particularly interesting, I highly recommend you take CS 450, the Computer Networks course, or 484, my Secure Web Application Design course, where we'll learn a lot more about how these things work, how to make them secure, how to make them efficient, all that fun stuff. Thanks so much for watching, and I'll see you next time.